Let's try another problem. An air-filled capacitor consists of parallel plates, each with an area of 7.6 square centimeters, separated by a distance of 1.8 millimeters. If a 20-volt potential difference is applied to these plates, calculate A, the electric field between the plates, B, the surface charge density, C, the capacitance, and D, the charge on each plate. Here's a sketch of the capacitor. It's got its plate separation of 1.8 millimeters. I'm going to convert that to meters. And it has a plate area of 7.6 square centimeters. I'll have to convert that into square meters. We're asked the electric field between the plates. I'll remind you that the electric field is equal to V divided by D. And we know what V is. It's 20 volts. And we know what D is. It's going to be 1.8 times 10 to the minus 3 meters. So let's put those numbers in. I get that the electric field is just over 11,000 volts per meter. That's the answer to part A. B, the surface charge density. What is meant by surface charge density? In other physics texts, you're going to see surface charge density represented by the symbol sigma, a lowercase sigma. That means how much charge there is per square meter or square centimeter. Surface charge density is the density of charge on the surface of the plates. In order to figure out the surface charge density, we need to know how much charge there is on this capacitor. The plate area we're given already. Now, we could figure this in terms of coulombs per square centimeter or coulombs per square meter. Let's look and see how we're going to get the charge first. We have to figure that out from the capacitance. I know that Q is equal to C times V. And I know what V is. I have to look at what the capacitance is. The capacitance is given by epsilon naught area divided by the plate separation. So I can say Q is going to be epsilon naught A over D times V. Let me take that and plug that into my surface charge density equation, and let's see what comes out. It looks like my plate areas are going to divide out, and so that I'm going to have that sigma is equal to epsilon naught V divided by D. And I know all those numbers, so let's put them in and solve for them. Let me remind you that a volt is the same as a joule per coulomb, and a joule is the same as a Newton meter. So I can write a volt as a Newton meter per coulomb. Let me make that substitution here. Newton meter per coulomb. And let's look at the units first. Looks like a whole bunch of stuff is going to cancel out. I'm going to have a coulomb that cancels there. I'm going to have a Newton that cancels here. I'm going to have a meter that cancels with the meter downstairs. And it looks like my units are going to be coulombs per square meter, which are the units that I'm going to want. So let's put in the numbers. I get that the surface charge density is 9.83 repeating times 10 to the minus 8 coulombs per square meter. Now we need to figure out the capacitance. Let's just use our capacitance equation. We're going to have to make conversions from square centimeters into square meters. I've put a conversion factor upstairs that 1 meter is equal to 100 centimeters, and I have to square that because I have square centimeters. Now let's look at the units, and then let's do the numbers. I'm going to have centimeters squared cancel with these centimeters squared. I'm going to have these meters squared cancel with those meters squared. I'm going to have a coulomb squared per Newton meter, and I hope that that turns out to be a farad. I get that the capacitance is about 3.74 picofarads. Finally, let's figure out what the charge is on each plate. Q is equal to C times V. And I find that there's 7.5 just under times 10 to the minus 11 coulombs, or about 75 picocoulombs on each plate. Let's take a look at the next problem. Here's the last example. A parallel plate capacitor is to be constructed using Pyrex glass as a dielectric. If the capacitance of the device is to be 0.2 microfarads, and it is to be operated at 6,000 volts, A, calculate the minimum plate area required. B, what is the energy stored in the capacitor at the operating voltage? For Pyrex, use kappa equals to 5.6. Note, each dielectric material has a characteristic dielectric strength, the maximum electric field the material can withstand without electrical breakdown or rupture. For Pyrex, the dielectric strength is 14th times 10 to the 6 volts per meter. Wow, there's a lot going on in this problem. Let's suppose that we've got ourselves a capacitor with Pyrex in between the plates. I suppose that you know Pyrex is a kind of glass that is very resistant to changes in its dimension when it's heated. So it's used in casserole dishes and laboratory glassware in which heating occurs. It has a very low coefficient of thermal expansion, which is one of the very last topics we'll take up in this course before reviewing for the AP exam. So I've got Pyrex in here. Let's suppose that this Pyrex is operating at its maximum dielectric strength because we're trying to figure out what the minimum area is that is needed for the plates. So we're going to say that the maximum electric field that occurs is 14 times 10 to the 6 volts per meter. I'll have to recall that E is equal to V divided by D, so I can say that the voltage is going to be E times D. So I know what the voltage is, it's 6,000 volts. I know what the capacitance is, it's 0.2 microfarads, and so I could use those to figure out what the minimum thickness D is going to be. Let me write down my capacitance equation. C is going to be kappa epsilon naught A divided by D. Now I'm trying to figure out what the minimum plate area is, so I want to solve that equation for the area. Over here I could figure out that D is the voltage divided by the electric field, and I want to make that substitution over in this equation where the electric field I'm going to use is the dielectric strength of the Pyrex glass. And now I can put in the numbers. Now I've got a whole mess of units here. Let's see what cancels out. Let me do a quick side calculation over here. We have Q is equal to C times V. So in units, C is going to be Q divided by V. So the units of farads are going to be the units of coulombs per volt. I'll use that over here. A farad is equal to a coulomb per volt. Let me make that substitution over here. Let me also realize that a volt is the same thing as a joule per coulomb, and a joule is the same as a Newton meter. So I've got a Newton meter per coulomb for a volt. So let me work through these units again. A volt here and a volt here. I've got a coulomb here and a coulomb there. Now let me take this volt and let me turn it into a Newton meter per coulomb. And now I've got a meter that cancels a meter. I've got a Newton that cancels a Newton. I've got a coulomb that cancels a coulomb. And I'm left downstairs with units of 1 over meters squared, which will come upstairs for meters squared. So my units work. Let's put the numbers in and figure out what the area is. I get that the area, the minimum area, is going to be 1.73 square meters. That's a huge area, but that's the number that we get. What that means is that it may not be realistic for me to be able to make a 6,000 volt capacitor using Pyrex glass as a dielectric. That's the answer to part A. In part B, I'm asked what is the energy stored in this particular situation, and I'm going to use that U is 1/2 CV squared because they told me what C was and they told me what V was. 1/2 of 0.2 times 10 to the minus 6 farads times 6,000 volts squared. Let's put in the numbers. I get that the energy stored in this situation is going to be 3.6 joules. So, to review, we've talked about capacitors, we've discussed their important equations, we've talked about the energy that's stored in capacitors, what happens when there's a dielectric in place, and we've solved several non-trivial problems and a couple of ones that are easier. You know the problems are going to get more difficult than the example ones, and I've tried to illustrate some of those more difficult problems here. For now, that's it.